All right. Hello, everyone. Welcome to the special edition of CS251. I don't know what to call it. Interview series number 2. You're our second guest after Ryan O'Donnell. Thanks for coming, Pravesh.
Thank you for having me.
Really, really great pleasure to have you here. It's always fun to talk to you. I have some interesting questions for you. I want to learn more about your research area and some other things that you like, you enjoy. Let me actually start by asking you how you would describe computer science and theoretical computer science, because I think everyone has a bit different view on this, and just like getting that perspective is very interesting to me to hear like different theoretical computer scientists describe their own field in simple terms. I think it's fun. So how would you describe the field?
Yeah, it's definitely hard, I guess, to describe computer science. Partly because, I guess we get siloed into, various sub-areas of computer science early on, etc. And partly because I think computer science has been in great flux. Computational biology, for example, probably wasn't a part of computer science 20 years ago, probably didn't even exist as a field, but it's a full-fledged department that we have here. So
we have a new major now in computational biology.
Exactly. Yeah. And I'm sure areas will keep getting added on. So maybe a broadest view to maybe define may basically just involve something like study of computation, applications of computations, technology that relies on computation, and
And what is computation?
yeah, it's again extremely hard to define in. So when we mean computation, we usually talk about what's going on in our digital computers, or what might be going on in our phones or tablets or whatever. But as we all know, and as 251 students, I guess definitely computation is much more general.
Right.
Computation is basically just like a set of rules that act on some small set of particles, small set of atoms, small set of variables, whatever. It gives like a set of evolution rules, and computation is a study of what would happen in the future if you simulate these rules for a long time. And we have several models to understand this: Turing machines and digital computers. All of them are like embodiments of this phenomenon that there's a whole lot of particles, and there is a set of rules by which they evolve. The only restriction on the rules is that they are local. And in some sense, every process where this goes on could be thought of as a computational process.
In different contexts, those rules can be different.
Exactly.
And even like maybe you can also study like small fundamental particles, but also maybe higher level emerging things like economics, biology, and see these rules.
Absolutely.
evolve,
Yeah. So these rules, as you said, could describe fundamental pieces of the universe. Indeed, in fact, our physical laws are really stated in that form, right? Like physical laws are about stated in terms of differential equations, which are in some sense local evolution rules. They say, if you have like a bunch of particles acting together, what would happen to them? If you simulate them for like a infinitesimal time step.
Right.
And so they almost are described by means of describing these local rules. And as you said, the same thing can be thought of. At least there is a computational perspective or computational way of viewing even large-scale phenomena like markets with rational agents, or I don't know, like laws of how billions of gas particles interact together, etc. So these can be at various levels, various scales, number of particles, size, everything could vary. But I think the constant is that there is.
And what is theoretical computer science?
I guess I mostly even talked about theoretical computer science, even I guess when we were answering this question. I suppose a computation, like theoretical computer science, I would say is a study of computational phenomena.
Right.
It's like it's a scientific study of how to model, how to study computational phenomena broadly construed. Of course, they include phenomena going on in our digital computers, and phenomena going on in the latest software, but they are obviously much more broad.
Rigorous, that like mathematical, like we prove theorems, right?
Yeah, I guess one could, depending on your perspective, one could, agree or disagree whether that is a fundamental aspect of the study of computation. Like presumably you could have a study of computation which is less rigorous.
Right.
Where, for example, P not equal to NP is a law of nature and not really a mathematical question. But yes.
As Scott Aronson likes to say, like if we were like physicists, we would declare P different from MP as a law of the universe and be done with it and move on with our lives. But we have a more like a mathematician mindset, I guess.
Yeah, but you're right, though. I guess the predominant methodology to study these questions about computation is mathematical in nature. It's rigorous in nature. So we phrase our results as theorems, which are precisely described. We prove them using like rigorous mathematical methods. Right.
Actually, interesting. If it wasn't like that, like, how would you describe, or what kind of options might there be to study computation? Not mathematically rigorously, perhaps, but still, in somewhat rigorous way.
I would say we don't even have to somehow think of a hypothetical here, right? Like there are studies of computation going on right now, large projects which actually do study computation in maybe a slightly different way than maybe theorists approach this question. For example, look at deep learning, right? There is a whole, we have several experts in our department, and there are experts all over the world who are trying to understand, what's happening in deep learning. Why are these deep networks so successful in solving problems that arise in practice? Why are we able to learn them despite several computational hardness results? And early on, people realized that if you want to somehow approach these questions theoretically, you would have to work with like, toy models. And that's a reasonable approach. And then there were this other set of experts who realized that maybe we can actually study actual networks, but maybe, instead of trying to prove theorems about them, we could just run them and see what happens.
Right.
So it's like a very, I guess some people like to call it the phenomenological approach of studying deep learning. And, in some sense, you could view it as maybe a slightly experimental way of studying,
Right.
some kind of computation, namely deep networks going on, in several of the applications.
Okay, yeah, maybe we can go into that a bit deeper later. But let me actually let's get into like your research more. And you are interested both in like in theoretical computer science. We usually like to divide into like two camps. Like there's the algorithms theory people, and then there's the complexity theory people. Algorithms theory people are trying to prove algorithms and upper bounds. Complexity theory trying to prove lower bounds and possibility results. You are interested, I would say, in both, and you fall maybe under in both camps at the intersection. And from the upper bound side, I guess you are trying to study these big hammers, like I guess, right? So like these general techniques, algorithmic techniques that can hopefully solve a large class variety of different problems. So yeah, I want to talk about that, but also then I guess from the lower bound side, and correct me if I'm wrong here, but maybe your point of view is that, look, we don't know how to prove lower bounds. So instead of proving lower bounds, like ruling out any kind of algorithm, let's restrict ourselves to these general powerful algorithmic techniques and prove lower bounds against those classes of algorithms. Is that a fair characterization of like the general?
Yeah, actually, let me maybe comment a little bit about this last point. Because there's maybe an interesting discussion. It's an interesting distinction between like the goals for proving lower bounds. So, P versus NP, like whether P is different from NP is a lower bound question, right? Like it's a question of lower bounds on polynomial time Turing machines. And so presumably when you think about it, it's a question about proving a limitation of a certain class of algorithms, namely all polynomial time algorithms. So one goal of proving lower bounds is to, basically delineate what can certain classes of algorithms do. Right. Of course, one of the most general being P versus NP. But there's a different goal of proving lower bounds, or maybe just a different perspective on lower bounds, which is to ascertain which problems are hard and which problems are easy. Mm-hmm. Okay. And now, in theory of computation, we usually focus on the first aspect. We are not maybe overly interested in a particular problem.
Correct.
The problem is somehow almost incidental. What we're really interested in is in showing that, hey, there is a problem in NP that, polynomial time Turing machines cannot solve. And there are like lower instantiations of this phenomenon all over. Like prove that there is a function that's like easy in some sense, but is not computable by AC0 circuits or whatever, right? Like it's really, I guess the point is that the focus is on the computational model, not the problem. Mm-hmm, mm-hmm. But there's a different way to view lower bounds, which is to ascertain, hey, let's say I'm interested in this problem.
Right.
How hard is it? And when is it easy? And what makes it easy? And so one other purpose of proving lower bounds is to ascertain when does a particular problem become hard, or is it hard, and can we expect it to be hard, and so on. And I guess my work really looks at this view, this goal for proving lower bounds. For example, if I ask you, hey, let's say I give you like a graph. Let's say it's even a random graph. It doesn't matter exactly what it is, but let's think of like, graph where the edges, let's say, are present independently with probability half. And I add like a large click to it. And you ask, well, can I detect that large click? Or when can I detect it? Now, the goal in proving lower bounds for this problem is to really ascertain, the limitations, the hardness of the problem more than the limitations of a certain algorithm. And so it turns out that, we are really bad at proving lower bounds. I guess that's the fact that I mention a lot in my class, and I'm sure you mention a lot in your class. We only have like stories and conjectures, to
Nice stories.
Nice stories and good conjectures. But nonetheless, we don't have any definite piece of knowledge. And I guess the question is, in the absence of a definite piece of knowledge, in the absence of like definite techniques to ascertain when a problem becomes hard, what should you do? Well, you could give up.
Right.
But computer scientists almost never give up. If a problem fails them, well, they modify the problem and solve it.
Yeah.
And so I guess in this particular context, I think the perspective I have is that, instead of trying to prove lower bounds on all efficient algorithms, let's draw a boundary around the techniques that we do understand.
Right.
And that we agree that maybe is more or less the best we've got at the very least so far.
Right.
And see if we can prove lower bounds against the best algorithm that falls into that category. So I won't rule out all polynomial time Turing machines for finding clicks in random graphs, but maybe I'll be able to rule out, some large enough class of algorithms that we have good reason to believe includes everything we've got. And if I can prove that, then that can be taken as evidence of hardness of the problem.
Yeah. So I want to get into some of those general techniques, powerful techniques. But before that, I want to touch on something you mentioned, which I find interesting. So you, for example, consider the random graph input. So in some sense, you're not really looking at worst case analysis here, but you're considering a randomly chosen input. And I guess when you fix a problem, then you're like, let's look at maybe a family of distributions and see like, maybe it's like parameterized. There's maybe some parameter P, you're choosing the edges with probability P, for example. And then you can see as I now take P from 0 to 1, at what point does the problem become hard? When is it easy? So can you say a bit more about that? Because this is not something, especially in an intro theoretical computer science course, we don't really touch upon this. Yeah. We're doing worst case analysis, but of course that can be criticized. Like, why just worst case? I mean, we focus a lot on it. Mainly like it's mathematically much cleaner, easier to understand. But yeah, maybe you can tell us a little bit about average case analysis, what that means, what do we know, how does it compare to worst case analysis, and so on.
Yeah, I guess that's a really good question. Yeah, so I guess in intro classes, we don't focus on, anything beyond worst case analysis so much. There is a natural criticism of worst case analysis, as you said, which is that, well, maybe, SAT is hard only because there is this one bad family of instances. And if you remove them, like everything is basically great and, you can solve SAT in polynomial time, presumably. That's like a reasonable criticism. And, maybe you want to correct that. That would be one goal. But actually, more generally, I think there are situations where, we naturally need not just, worst case hardness of a problem. We need like a way to efficiently sample hard instances or efficiently obtain hard instances. And, maybe it's hard to describe in details, but, in cryptography, like we are often faced with this problem. Like, cryptographic schemes are often based on, hardness of solving a certain computational problem. And the scheme involves using a certain instance of that problem in order to do some, cryptographic protocol, like, maybe you're encrypting a document or whatever, right? Mm-hmm. Now, worst case hardness of the problem doesn't really give you much because, the instance you sample could be easy. And so you really need that, the instance I have should be, hard.
Which typically is a random. In cryptography, we typically choose random. Right?
Exactly. And so, there may be those couple of reasons to maybe think about, instances which are chosen from some natural probability distribution over the space of all instances instead of like worst case instances. I would say, there is like even better reason in some sense to consider this. I guess there are lots of applications and lots of application-oriented reasons to consider, what happens to computational problems when the inputs are random. But I think maybe the biggest reason would be that there is a lot more structure to uncover than we typically see in worst-case problems. And so, if you are like a theorist of computation, if you are interested in the phenomenon of computation, then, there's just like so much more for you to learn when you look at random instances. I
like that. I mean, I actually like that from a I'm putting my mathematician hat on. I'm like, oh, that sounds very good. Like, I mean, I want to understand the structure of the problem. And in order to fully understand the structure, I cannot just focus on worst case. I should be also looking at...
And in fact, that happens, right? Like, for example... it turns out, just to give you an example of a result, when we consider SAT problems, when we consider, let's say, instances of, let's say, 3 SAT, where all the clauses are, size 3, we never mention how many clauses there are, and we don't actually think that the number of clauses matter, right? But it turns out that when you consider random 3 SAT clauses, like instances where 3 SAT clauses are generated at random, it turns out that how many clauses you have really changes the complexity of the problem. In particular, it may even appear counterintuitive, but if you have more clauses, the problem becomes easier. And in fact,
too many constraints. Too many constraints, actually, and maybe if you think a little bit more about it, it becomes apparent that if you have too many constraints, it'll become easier to just like prove that, hey, you know what, there's no way to satisfy it. Right.
That's exactly what's going on. But it turns out that there's a very non-trivial threshold, such that if you have more constraints than that threshold, then the problem becomes computationally easy. At least so far as we know. Yeah. While below that, it's like, in some sense, as hard.
So we're looking at the number of clauses to number of variables.
Right. That's the formal way to describe it. Like, as you know, we are dealing with asymptotics here. So we've, got to think about growing number of variables. And then the question is like, as a function of the number of variables, how many constraints do you have? Now for like, not having trivialities, there are almost always at least linear number of constraints. You need to have at least n constraints to actually have the problem be somewhat sensible.
Right.
But it turns out that, if you have many more than n constraints, it turns out for 3 SAT that magic number is n to the 1.5. Turns out that the problem is actually easy if the constraints are chosen at random. And this is a kind of, structure that we don't quite see in worst case analysis.
Yeah.
But when you ask the question about average case, you suddenly like,
so what is known in the 3 SAT case, like up to n to the 1.1 over 5.
1.5.
1.5. We know that it is easy.
Yeah. Okay. So let's maybe.
So what is like? Where does it become easy, hard?
Yeah, it's like.
And there's a sharp threshold, so I want to get into that a little bit.
In fact, like 2 sharp thresholds. It turns out.
Okay.
Like if you take a random 3 SAT instance. As you correctly pointed out, like, there's this very intuitive way to understand that if I have, more and more constraints, at some point, the instance is going to become unsatisfiable because, I'm choosing constraints at random, I'm going to rule out essentially every assignment eventually. So it turns out that you can ask, well, the natural question to ask is how many random constraints do I need where, the instance becomes unsatisfiable? Right. And it turns out that, this number is something around 4.27. So it turns out that if you have more than 4.27 constraints, the instance becomes unsatisfiable with high probability. That's the first phase transition.
So where does this number come from?
Yeah, it's a really good question. And first of all, just to tell you the status of our ignorance, we don't actually know how to prove that there is such a threshold, such that for every n, we don't know how to prove that there is a constant C such that for every n, if I have more than Cn constraints, then, the instance becomes unsatisfiable, while it's less than Cn, then it becomes, satisfied. We know that for any given n, there is such a constant, but for all we know, this constant could, depend on n. That's maybe some worry. It's almost, it's something that, everybody believes in. This is called the satisfiability conjecture. It's been proven for not 3 SAT, but for like K SAT for large K. But for 3 SAT itself, we don't quite know whether this is true, but we kind of think it's true. There is like an asymptotic function of large K that basically gives you some constant here, but I think this constant is most likely experimentally determined.
Okay, so then what else do we know?
That's the phase transition. That's the first phase transition. So now you can ask, let's say, I give you 5 times n constraints, comfortably above this 4.27 n limit.
Right.
And so the instance is going to be unsatisfiable with high probability. So you can say, okay, what are you asking me? There is nothing to return. You could just say unsatisfiable. But let's say, I ask you to give me like a short witness, like convince me. I give you this formula. It has 5n constraints. Convince me that it's unsatisfiable. Yeah,
it's interesting because let's say you have an algorithm and your algorithm says, hey, your SAT instance is not satisfiable. You're like, am I supposed to just believe what you just said? Or can you give me a convincing argument that it is actually unsatisfiable?
Right, precisely. I mean, a priori, it might appear like a weirdo question. It's like, why do we even care? But as you said, For a random instance, I could just always tell you unsatisfiable, and I'll be right like 99% of the time or whatever.
Yeah.
But it's also not interesting. And, I'm saying nothing about the instance at hand. And somehow, I guess in order to give you something meaningful, I have to give you like some short, convincing proof that here is the reason why I believe that this, clauses cannot all be satisfied together. And, this doesn't need to be anything fancy, right? Like you might just produce like a set of 3 clauses and you say, hey, you know what, any assignment that satisfies the first 2 must violate the third. And, this is a short proof because it relies only on looking at 3 clauses and, they can only involve like 9 variables.
Right.
And, I can just check for myself because there are like at most 2 to 9 possible assignments.
Sure. Yeah.
So if you showed me like there was like a short violation, like a small number of clauses that one of them must always be violated, well, that's a, proof that proves to you that, the instance is unsatisfiable. So you could ask, okay, is there such a short witness? Not just these kind of certificates, but you could ask like all kinds of certificates, like any certificate that a polynomial time Turing machine could find, for example.
Mm-hmm.
And it turns out that we do not know any certificate, any convincing proof that can be found by an efficient algorithm below n to the 1.5. So, unless I have more than n to the 1.5 random constraints, I don't know how to do this. In fact, there's like this famous conjecture made by computer scientist Uri Feige, which says that there is no such algorithm. And, just like in our courses, we start from hardness of 3-sat and prove like tons of hardness results by means of reductions. You can start from Feige's conjecture and like prove hardness of several like, problems on random inputs.
Oh, nice. So this has applications, this conjecture. Then through reductions, we can get for other problems, other kinds of thresholds.
Yeah, it's like, it's a lot, we weave a web of reductions in our complexity classes. Like, you do like this first proof of NP completeness and then suddenly like, a host of problems become NP complete. It's not that successful. It turns out that there is like an inherent limitation to reductions in average case. And the reason is very simple. It's like, if you remember your reductions, they are like, they basically replace like a vertex or whatever by like, some constant number of variables or whatever, right? And it turns out that this process really modifies the distribution of instances. Like if you start from a random instance of, let's say, 3 coloring and applied your standard reduction to 3-sat,
you don't get a random.
You don't get a random instance. You get like a really pathological distribution, in fact.
So we don't have a clean completeness, hardness.
Unfortunately, not. But I guess I would say,
is there notion of complete? Is there a complete problem for like average case?
It's I guess one could try to define some reasonable notion of completeness, but I guess in some sense we don't. Yeah, I guess the notion of completeness becomes interesting when we have, I guess, enough reductions to play with.
Right. Because
in some sense the reductions and the power of reductions is so limited, it seems like you may end up defining like an overly small complexity class, like maybe a complexity class with 2 problems or 3 problems.
Empty set.
Yeah, but people always have one problem, the one you've chosen to be complete.
Actually, let me backtrack a little bit because I want to get into like when we talked about these sharp threshold phase transitions. This intersects with statistical physics, and physicists are interested in this, right? So can you talk about the intersection there? And I guess like there's some interesting results that physicists have proved in quotes, maybe.
Yeah. It's actually super cool because physicists have been doing this longer than us.
Right, yeah. So in physics, like what does it mean, phase transition?
Right, it's a great question. So, okay, I'm not a physicist, so I don't completely understand the motivations, but it turns out that you can use, let's say, random 3-sat instances as models of certain physical systems. So I know that these are considered as toy models, and the official name for them is like spin glasses or whatever. Mm-hmm. And the rough reason is quite simple. Like maybe the analogy that every textbook gives is the following. Like imagine that you have like a magnet, and we imagine there is a model of magnets where like magnet is made of like really, really tiny magnets. And like if you take a piece of iron which is not magnetized, then these tiny pieces of magnets are like completely misaligned.
Okay.
while in a magnet, like these are all like completely aligned. So like in the poles all point to the same way. So now, imagine like a situation where there are like lots of these tiny magnets and they interact with each other. And so like magnets, exert some force, the magnetic force or whatever, on like nearby magnets. So for example, this magnet would try to align the magnet near it in a way so that its poles are completely correctly aligned or whatever, right? So there's some interaction between like these small magnets.
Right.
And, you're supposed to view it as a certain 3-sat clause which captures the constraints that, the interaction between magnets is posing on their position. Like, for example, some configurations of magnets are clearly ruled out, right? You can't have a tiny magnet, which is like, where like, let's say this is the, this is like, what is it? I even forget what the poles are called, but let's say it's like positive pole and negative pole or whatever. Okay. And let's say, imagine that I keep the positive pole of the second magnet near it. Well, this would be a configuration where they will repel. So like this, the second guy would like turn, right?
Okay.
So we know that this configuration is not stable. So you could think of it as like an unsatisfying assignment for a clause.
Okay.
And so anyway, like that's a level of detail I understand this with, but for whatever reason they've arrived at, models 3-sat as like model of these constraints that tiny magnets exert on each other. And, the satisfying assignments now correspond to the structures that these tiny magnets will arrange themselves in.
Stable arrangements.
Right,
okay.
Exactly. And so now you can see like, finding a satisfying assignment or proving facts about their structure, etc., could potentially relate to, talking about how magnets will arrange themselves. Now, they realized that this is all great, but, so far there is no randomness. What they realized was that, what kind of instances of 3-sat should they study? And for physical reasons, they thought that it can't possibly be like arbitrary instances. That's not how actual things work, apparently.
It's not going to be worst case.
It's not going to be worst case.
Yeah.
I said, okay, a reasonable model is when I have, random 3-sat constraints and with like, some constant times n number of constraints. And this constant is typically like much less than this 4.27 magic number.
Okay.
So, there is always a configuration.
Okay.
The magnets can arrange themselves. So, they were clever about this. So like the first phase transition is like really important to them because it, really tells them what is a good modeling choice to make. Like if you want to model magnets, they've got to have like a stable configuration.
Yeah.
So you have to choose like a satisfiable instance, and they chose, a random 3-sat instance with like sufficiently small number of constraints so that it always has a satisfying assignment. And then, they study various questions about how the solution space to these random 3-sat instances looks like. And I think the motivation is that, they are saying something about reality. Like they're saying something about, how magnets will arrange themselves. And it turns out that they are like, the structure of the solution space changes as you vary the number of constraints. And this is all happening, below 4.27. So it's like, even below that, there are like a whole lot of phase transitions. So it turns out that at the very beginning, there are like many, many solutions. Because there are very few constraints, you can imagine that there are many, many solutions and they're like all spread out.
So is it like the number of solutions? There's like jumps in the number of...
Number certainly, but even like how, like there is even a geometry of them. Like for example, you can define distances between solutions, which is like, how many bit flips do I need to change one solution into another?
Right.
And that's like, that gives you some distance between solutions. So it, you can arrange these solutions on the space now.
Right, yeah.
Based on distances. And you can talk about the geometry of them.
Okay.
And it turns out that, as you grow the number of constraints, certainly the number of solutions falls, but it also turns out that, they arrange themselves in weirdo geometric patterns. So it turns out that there is a so-called clustering transition where, there are like multiple clusters of solutions. Clusters are all far apart from each other, but each cluster has multiple solutions, which are all like somewhat close to each other.
I see.
Etc. Yeah, it's
very fascinating.
Yeah, exactly. Now that's all great. That's all physics, right? You could say, well, where does computation come in? Well, it turns out now you can ask the question of finding a satisfying assignment for random 3-sat instances, right? Well, the worst case instance is a hard problem, but you can ask it about random versions. It turns out that the geometry, the facts about geometry of solution space relates to how good our algorithms are in finding a satisfying assignment for random instances. This is the key connection. And so, for example, physicists invented their own algorithms.
Okay.
And, they studied them experimentally and heuristically and, all sorts of, maybe not completely rigorous ways, but, pretty precise ways, and made pretty precise conjectures. And I have to say, like, many of their conjectures have been verified over the years, etc. But yeah, eventually the question, became about what is the connection between the computational easiness or hardness of solving random three-set instances, and how does it relate to, these geometry transitions that are happening in the solution space. Again, I don't exactly know how this relates to magnets eventually. But, you got me in when you talked about computation. So
beautiful stuff. Yeah, that's fascinating. Definitely. I mean, we could go there and talk about that, but let me actually backtrack some more because we have other interesting stuff to talk about. So these like general algorithmic techniques, one, I guess, very well known one, although 251 students probably don't know it yet, but linear programming would be like a very powerful technique. So maybe we can describe what linear programming is. Maybe we can start with integer programming, go to maybe semi-definite programming. And then tell us like what these techniques are, and then we can maybe go a little bit more into like your work and what you've done in that space. I guess so. We I guess we don't do linear programming in 251, but I suppose we do it in 451. That's correct, yeah.
And I guess it's really simple, right? One of the basic primitives that we learn very, very early on is how to solve linear equations. It's like, if I give you a bunch of linear equations, there is a way to solve them. Now, I guess in grade school, we learned this, we learned actually multiple algorithms. I guess I learned the one where you take two variable equations, draw lines, and like find the point where they intersect, or like, say that they're parallel or whatever. But there is actually a polynomial time algorithm. It's slightly non-trivial to prove its polynomial time, but we do know its polynomial time, that solves linear equations in, let's say, a growing number of variables. So if you have like n variables and let's say, m constraints, where m is, think of like m as like n or n square or whatever, then there is like, a polynomial time algorithm. In fact, it's a cubic time algorithm that can solve these equations and, tell you if there is a solution and, report if there isn't. It's called Gaussian elimination. And that's great. And it's an extremely important primitive. Like you can almost imagine that solving equations would occur many, many places, but there's like a generalization of it, which again, a version of it we learn in school, which is like, instead of finding solutions to two variable equations, finding solutions to two variable linear inequalities. Like imagine that I give you inequalities like 2x plus 3y is bigger than 1 and 3x plus 2y is bigger than whatever 0 or whatever. So these define some half planes. Each of these inequalities is like there's a line, and you're looking at all points on one side of the line, and you're asking, if I look at these two half planes, and they intersect, well, is there a point in the intersection of these two half planes? That's what we're asking, right?
With two inequalities, we would have two, but with m, we would have m planes, and we want to look at the intersection of all of them, and is the intersection non-empty or not? Exactly.
That's the most basic question is like, is the intersection non-empty? And you may be even interested in solving the search problem, which is like finding a point in the intersection.
Right.
Now, you can ask these questions in any number of variables, and that gives you the higher dimensional version of these problems. It's extremely non-trivial, but it turns out that even for this problem, we have a polynomial time algorithm. Actually, this is extremely kind of mind-blowing because, we all grew up in like you and me, we all, grew up in a time where linear programming was always in P.
Yeah.
We don't remember that there was like a time where people actually thought that it could be NP complete. I suppose at least some reasonable people thought in the 60s that linear programming could be NP complete, and there was a reason for that. People were using linear programming to solve all sorts of problems. Like, they were able to reduce to linear programming all sorts of planning and production problems, like how best to allocate resources in a plan.
It can encode lots and lots of different problems.
It's extremely expressive in, what it allows you to encode. And so people thought it's so powerful, it's got to be NP complete because, we don't expect good things to happen to us. So when like Khachiyan proved it, proved that there is a polynomial time algorithm for it, was like it was a celebration. There's like I don't know, if you talk about this New York Times headline But New York Times almost wrote an article saying P equals NP. I mean, they didn't quite phrase it that way, but it's clear that they thought that, well, a breakthrough has happened. And
I don't know about this actually. Okay.
It's a brilliant article. You can go back to this time machine version of New York Times and you can look at it.
I'm going to check it out for sure. Yeah. Okay.
But that's linear programming. And Kachian's invention was 79. And people found like faster and easier algorithms, not just in theory, but in practice eventually.
Right.
And in the late 80s and early 90s, it became like an extremely powerful tool for not just like solving planning and production problems in factories, but like, even solving problems, algorithmic problems that people were stuck on for a long, long time. And this was especially important for this field called approximation algorithms. So it turns out that, several problems which are NP complete, it turns out that not all is lost for them. We can say extremely non-trivial things and give non-trivial solutions for them, even when we know that we cannot find exact solutions. It turns out that we can give solutions which are, in some sense,
close
quite
enough.
good. Exactly, close enough. And in finding this close enough solutions, in some sense, if there is like one technique that you want to give importance to, there are several results, but, if there was like only one name you had to take, like linear programming would be it. And so that's linear programming. And, it did wonders, but it turns out that despite efforts and significant efforts, it failed to solve this basic problem called max cut. I don't know if you talk about this in 251.
Yeah, absolutely.
Given a graph, just give me a partition of vertices so that the edges going across the partition are maximized. It's a really simple problem. There's a really simple way to get at least half of the number of edges. Just
doesn't get simpler than that.
Doesn't get simpler than that. It's like the very first randomized algorithm we teach. Yeah. You can make it deterministic if you like.
I mean, it doesn't even look at the edge structure.
Yeah, it doesn't. Yeah, it doesn't even
flip
look at
a coin for each vertex. I don't care what the edges look like.
Yeah, it's such a great algorithm, right? Like, and it gives a non-trivial guarantee in the sense that it gives you, a cut with at least half the total number of edges in the maximum cut. In the 80s, I think, people were trying to improve on this algorithm. And believe it or not, they all failed. There is no better algorithm that people knew for this problem before maybe 94, 95. In 95, Gomans and Williamson, they found this magical algorithm.
This is one of the most beautiful results
it's a striking story, right?
Computer science, in my opinion.
Yeah, it's one of my favorite results too. Yeah. It begins like a string of my favorite results, and this being the first one. And so like Gomans and Williamson found an algorithm which actually gets you 87% of the maximum cut. Like it gives you a cut which is provably going to have at least 87% of the edges in the maximum cut. And 87% is like much, much larger than 50%, where we were stuck at. So it was like a massive improvement. And they did this, I guess in some sense, even more striking was the fact that they did this not via linear programming, but by, a tool, which is in some sense a generalization and a strengthening of linear programming called as semi-definite programming. And, maybe it's not the best to try to describe it because, we don't have a whiteboard or an iPad or whatever here. But you can think of it as like a generalization where, the inequalities are, instead of being linear inequalities, they're like inequalities in matrices of some form. Okay, and there's a way to talk about this, etc., etc. But
can we say it's like quadratic now?
Yeah, it's a class of
quadratic. Not all of them are going to be solvable, but it's like a subclass, let's say, of quadratic inequalities.
Yeah, absolutely.
That we know how to solve.
Exactly, yeah. So it turns out that there are some correctly defined and well understood class of quadratic programs, meaning all inequalities are like not linear equations, but like quadratic inequalities now. And not all quadratic inequalities can be solved, by the way. It's NP hard. Yeah. But some of them happen to be easy. And that's exactly what SDPs or semi-definite programs can solve. And Gomans and Williamson used this technique in this mighty powerful way to get like this 87% approximation result. It's like
beautiful.
It opened the floodgates to like a whole new class of algorithms. So what I think about is in some sense a generalization of this semi-definite programming technique. I guess that's one one-line way to describe, I guess, what I do.
Yeah, so let me now connect this to proof complexity, because I guess like one of the techniques that you use to let's say, prove lower bounds against linear programs or STPs, or even proving upper bounds, is by relating all of this to proof complexity, it seems. Yeah, it would be great to learn a bit more about that connection. So in 251, we start with mathematical proofs. Like we start our story with the fact that, in early 20th century, late 19th century, mathematicians wanted to put mathematical reasoning on a solid foundation. So they came up with this axiomatic systems. So that's a proof system. And that led to the birth of computer science, because that forced us to actually rigorously define what an algorithm is, what computation is, because mathematics that we do is going on here, and what we're doing here is computation. So it turns out that to define rigorously mathematics, mathematical reasoning, we need to do that and define algorithm. And that was the birth of computer science. And then later, computer scientists basically, we can say like they generalized the notion of proof system, right? So it's not just, you don't have to just look at ZFC axioms and see what you can derive in that system. Well, that's one system, that's good. But this whole thing is a computation. So yeah, what's our way? What's a computer scientist's way to define a proof system?
Yeah, it's a great question. Somehow, I guess I always view these things as, like somehow mathematicians studied proofs for a long, long time. And, they tried to formalize, what logical system these proofs are in. But I have to say, it's computer scientists who really thought of proof itself as a mathematical object. It's like, let's study this object called proof. Mm-hmm. And let's study how hard it is, how complex it is, etc. And so, maybe the simplest thing is to start from, this class NP that we both teach.
Yeah. So it's interesting, actually. Let me interject a little bit.
Yeah.
So it's really like when you want to formalize this process, it seems like enough to actually let's look at the proof verification process.
Right.
Let's just like formalize that.
Right.
And if you just think of it in that terms, you can say, okay, well, if you want to formalize proof verification, okay, then, well, we have axioms, we have derivations from the axioms, and someone can then check that the derivations are correctly applied. That's easy computation. And then, as computer scientists, we're like, okay, well, that verification process, you just can think of it as an arbitrary computation, efficient computation. Right. You don't have to really think of it necessarily as like deriving from the axioms, right? And then you sort of get to the definition of NP naturally in that way. So I just wanted to add that. I think like just focusing on the verification process is a good way to think about it.
Yeah, so I guess, maybe it's a key computer science insight to classify the kinds of proofs by how hard a computation you need to do to verify it.
Right.
Like somehow, it's not the proof, but the verification that's somehow the focus. I guess once you adopt that perspective, in some sense, I guess Cook did really have this perspective, in fact, when he was even, building this whole theory of NP completeness and writing his famous paper. By the way, this is 50 years of his famous paper.
50th
This
year?
is the 50th year, yeah.
We should have done something special.
Yeah, 50th year of the famous Cook-Levin theorem.
Okay, that's amazing.
Yeah.
Wow, that is important. Are there like celebrations going on somewhere?
I know that there is like a special segment planned in the Theory Fest this year.
I see. Okay, good.
Yeah. So yeah.
Look forward to it. Okay.
Yeah, but it's interesting because that's also how I think of algorithms. Even though I guess I have been advised by algorithm designers to not think of it this way. Here is how even I view algorithms. Like when you think of you say, okay, when I look at a computational problem, and if you took 251, the first question you ask, even if your goal is to design an efficient algorithm for solving the problem, the first question you ask is, can I verify a solution to it? It's like, it seems like a maybe not entirely on the route to designing an algorithm, but you ask it nonetheless, right? And then you say, okay, maybe like most of the time it's easy, to check if a 3-sat formula is satisfiable. Okay, somebody could just give me an assignment and I would just check if it satisfies all the clauses. And, then, we prove this NP completeness result. And we in particular derive that if there is an algorithm for, circuit sat or whatever, then, there would be an algorithm for every NP complete problem. And, you might remember how we do this proof. We basically take this verifier, the verifier that expects a certain kind of proof string and does some verification on it in order to convince itself that, the graph is three-colorable or the formula is satisfiable, right? And then we say that, hey, you know what? I can just take the computation of this verifier, think of it as a circuit, and, that gives me a circuit sat instance. And in particular, if I had a way to efficiently find an assignment that satisfies the circuit, I would be able to find a proof string that makes the verifier accept, right? And therefore solve the problem. So in particular, I guess what I want to abstract away from this is that if I gave you an NP verifier for a problem, there is an algorithm hidden inside it to even solve the problem. The algorithm is find the proof string that causes the verifier to accept. If you could efficiently find this proof string that the verifier accepts, well, that gives you an algorithm, to solve the problem. Right?
Right. So like we can brute force.
In particular, brute forcing gives you an exponential time algorithm.
Right. So that's how we get like NPs containing exponential time.
Absolutely. Right?
Right.
So here is the proof complexity insight. In the context of NP, we think of verifier as doing an arbitrary computation, arbitrary polynomial time computation. So it's like a Turing machine with like just time bound. But imagine that, we ask it to be a little bit more conservative. Let's say, don't do all these, fancy Turing machine computations. We only allow you to, do some restricted kind of checks. Now, by restricting the kind of verification procedures that the verifier could do, we restrict the power of the verifier. So certainly, we might not be able to, produce such verifiers for the problems that we know general verifiers for. But the upshot is the following. We could really implement this, weird idea for an algorithm into an actual one. The key insight is that if the verifier's verification process is somehow easy, then I could actually algorithmically find a proof string that causes it to accept.
Okay, let me say this again and see if I understand it correctly. So in the normal definition of NP, we don't restrict the verifier. We're like, look, this is a polynomial time verifier. And then the big granddaddy of all questions would be like, if we have a verifier, efficient verifier, general, can we actually also find the efficient solver?
Right.
Now you're saying, let's restrict the kinds of verifiers that we might have, right? So I'm going to restrict my verifier, efficient verifier, to be from some class, some natural class restriction. And then, so the big P versus NP question, okay, I'm not able to prove lower bounds there, sorry. But so are you saying that maybe now in the case of restricted verifiers that I might be able to, in some cases, maybe prove lower bounds, or maybe...
I'm actually talking about designing algorithms.
So now you're talking about designing algorithms. So
it's a crazy way to think of algorithms, but imagine, for whatever reason, your verifier, checked like a bunch of linear inequalities about, the proof string. Okay?
So you're saying that the verifier is such that it has this interesting property that the fact that it can verify also means that it can solve.
Oh, it's not so much as the verifier itself can solve.
But there's you can translate it into a solution.
So it's like, the key computational problem about a verifier is, given the description of a verifier, can you find input to it that causes it to accept?
Right.
In particular, if we had an efficient algorithm.
Satisfiable.
Exactly, right? And in fact, modulo this verifier, like algorithm to circuit translation, it's basically circuit sat.
Yes.
Right? And if we had an efficient algorithm for solving this problem, we would have P equals NP.
Yes.
Right? Now, we don't, and that's why we probably don't expect this problem to be soluble for general verifiers. But now imagine that I proved your favorite problem is an NP by giving a verifier.
Right.
And my verifier was like lightweight. It didn't do all kinds of fancy computations.
Sure.
It did some very simple checks. For example, imagine that it took this proof string and like checked that it satisfies some linear inequalities.
Okay.
And for whatever reason, the verifier has this property that if all those linear inequality checks were passed, then in fact the solution is in fact correct.
Okay.
Suppose this was true. Well, then I claim that you can even find a proof string that, makes this verifier accept efficiently. Why? Well, because we know how to find a solution to a system of linear inequalities efficiently. The problem of finding a proof string that causes this particular verifier to accept is same as the problem of finding finding a solution to a system of linear inequalities. And we just talked about linear programming. So you could use linear programming to, find that proof string. And that would give you an algorithm for solving the original problem. So it's like a crazy way to solve a problem. You first prove that the problem is NP, then say that, hey, can you do this proof while your hands are tied behind your back? Your verifier cannot do everything. Right. Your verifier is restricted to doing only like some specific kind of computations. And the upshot is that if you restrict the verifier this way, then you can solve this problem that we actually in general consider very hard, which is to find an assignment to the circuit that causes it to accept, or find an input to the verifier that causes it to, accept.
Very interesting.
This sounds like wishful thinking, but it turns out that not only are there non-trivial restrictions of verifiers for which you can do this, you can actually use it to design, best known algorithms for several problems.
So can you give us like a relatively maybe simple example that we could follow?
Actually I have a really simple example, I think. Okay. And this comes from statistics, because I guess I do a lot of statistics these days.
Good.
And so, let's say, you have a distribution, a probability distribution. And one basic problem that you may be concerned about this distribution is, can I estimate the mean of it? Right? You can imagine that you are given access to samples from this distribution. Sure. And you just want to take their mean.
Sure.
Now, this is an easy problem. It's like, it's very, very easy to design an algorithm for it. Just take the points, take their average, return their average. Yeah. And you know that if there are like sufficiently large number of points, you would actually do it right.
Right.
Now, imagine that I give you a slight little twist on this problem. I say, that before handing over these points or these samples to you, there's like a evil adversary who gets, between us, and they can modify 10% of the samples in whatever way they like. They can replace 10% of the samples by any other point. Okay. And they are basically actively trying to make your life hard. So they are going to do it in a way that, tries to fail your algorithm.
The way you describe it as like, is there any hope?
Excellent question.
Because if the adversary can make it any value.
Exactly. Yeah. In fact, as you observed, even if the adversary controls 1 point,
exactly.
10%, they can make it like arbitrarily far away from the mean. And that point really affects the mean a whole lot. Yeah. And, you are dead in the water, right?
Yeah.
But there is a hope, it turns out.
Okay.
And in particular, like this is the observation that I think basic statistics class maybe teach. Maybe they don't prove it in any reasonable sense, but they actually make this comment that median is a more robust estimator for whatever central tendency than mean.
Right.
This is the kind of claim that stats classes make. And it's actually very accurate in this context.
Makes sense, yeah.
Right? And somehow the intuition is that, either this evil adversary chooses their points which are like nearby the mean, in which case they don't matter. They don't affect the mean too much. Mm-hmm. Or they choose it very far away from the mean. In which case, if you take the median of the points, these far away points can't possibly affect the median too much, because you're looking like, in some sense, you're arranging these points in, on the real line and taking the median. That's great. Actually, this solves the problem in a reasonable setting in one dimension. But now, imagine that I ask you the same problem, except that the points are in like some high dimensional space. Mm-hmm. Like imagine that they are d-dimensional vectors. Mm-hmm. And you can think for a second if there is some reasonable notion of median, but there is not quite, because you can't quite lay down d-dimensional points on a line and like pick at the midpoint. Like on every line, the points have a potentially different midpoint. Mm-hmm. And so you can't quite do this. But it turns out that there is an algorithm that really relies on this, it's kind of crazy, but the best and the most general algorithm for this problem uses this proofs to algorithms methodology. Like, we really construct an NP verifier, if you will, for checking if, a given mean vector is actually close to the true mean vector. And then we show that the checks that you do to check if a given estimate of the mean is close to the mean, the checks that you do actually are simple enough that I can, basically write them not as linear inequalities, but as a certain semi-definite program.
I see.
And then solve it. Yeah, it's kind of weird that this, really wishful thinking way of designing algorithms not only works, but actually works to give,
It's
really powerful
fascinating. Yeah,
algorithms.
I mean, my interest is piqued for sure. I do want to learn more about this kind of stuff. It sounds fascinating.
Yeah, it's a complexity theorist dream, right?
Yeah.
Like, and maybe algorithmist nightmare, but
Very good. So I want to ask you about, like, in a lot of these statistical inputs, I imagine like your input distribution might be like Gaussian, so you're dealing with like real numbers, right? Distributions over the reals. And so I see this in your work and in other kinds of work along these lines. And I always find it very interesting because in some sense we know computation is a finite process, only deals with finite precision. We don't have infinite precision. Actually, before you and I get into that, I want to ask you a philosophical question, which is that, do you believe real numbers exist in the universe? Or do you think that it's just a good mathematical model to model what we see? What's your philosophical take on that?
yeah, it's a good question. I'm not sure I'll have like a superbly interesting answer for you, but I guess maybe my view is the following. I don't quite know what nature is like. I can't quite, I'm a very bad physicist. But I guess I have this computer scientist view of it. Like, if none of your experiments can distinguish,
Right.
between whether there are really, truly real numbers or just like very, very good rational approximations to them. If no experiment could distinguish, then like, who cares? It's like, if
Right.
none of your observations could ever check the difference between the two scenarios, then, I don't exactly know in what way can we even dream that there are real numbers. And so I guess the latter seems to be true, because every one of our experiments seems to have some kind of a finite precision. Even if like we get very, 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 very good at it, there is some fixed number of decimal digits we can calculate for any given physical quantity. And beyond which, in some sense, everything is fuzzy anyway. And so if that's the status of every experiment, then, the world is de facto rational.
Yeah, actually, like, let me ask you also about the simulation theory. Do you know about the simulation theory?
No, not quite.
So, this is the idea that we live in a simulation.
Okay.
And I guess that is tied with what we're saying here, because you might say, well, is our universe, the laws of physics computable? So in principle, could all of this be a computer simulation, which would seems imply that, things are, we don't have real numbers and like things have finite precision. I was just curious. Did you think about simulation theory at all? Do you have any?
I guess it's an interesting question. I've definitely encountered it in, sci-fi stories and I guess shows. I guess, I don't know exactly. I'm not sure I have an intelligent answer to it.
Yeah, I mean, it's just like if you have a particular, opinion one way or the other.
I do think that the processes going on in the universe, it is conceivable that, in fact, I do think that it's a computational process. And so in principle, it could be run on, on some giant computer somewhere.
Okay, but whether that is reality or not, I guess.
I'm actually not sure we can even have an experiment that will ever distinguish it.
Right,
the computer could be like a really, really good simulator.
Yeah, exactly.
And then, like in some sense, you would have to, like, for example, imagine that this is really the property that distinguishes the real true universe, from the simulation, that the simulation is somehow always like rational with like some fixed precision, while the real true universe is real.
Yeah.
And maybe we'll come up with like some experiment which has like really, 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 fine accuracy or whatever. And then we suddenly discover, oops, there is like zeros at the end of this.
Yeah.
Yeah, if that happens, maybe that would be
that would be amazing. Yeah. Okay, so now coming back, backtracking out of the philosophical territory.
Yeah.
So, what is the right model to deal with inputs that are real, like Gaussian inputs, let's say, and how does it really work with formal models?
It's a really good question, and like all models, there is this quote that I like all models are wrong, some are useful. Okay. And it's a little bit similar to this, right? Like saying that the distribution of data that we see is Gaussian is a modeling assumption. And the fact that Gaussians, will take values over irrational numbers or, vectors with irrational coordinates is like least of our worries in some sense. There are lots of properties of a Gaussians that are likely not going to be satisfied by any actual data that you see. Our hope is that, the distribution that we've chosen is just like a good enough model that when we design algorithms for it or, prove properties about it, they, faithfully carry over to the setting we are looking at.
Right. I mean, I guess my question is, how confident are you about the theorems being proved?
Exactly.
Because
that was his question about Gaussians.
Yeah.
But your question about computation is, I think, much more concrete. And I guess let's, for example, imagine that the world is Gaussian or whatever. Like the world gives you Gaussian data, and so now at least you're not worried about whether it's real or not. And you're asking, if I design an algorithm that does computation on real numbers, that's bogus.
Yeah, especially like if you have some corrupted data. And I mean, I guess when you go into the algorithm world, you are inherently working with rational approximations, and then when you start working with that, well, there's some error. How do you know that the error is not accumulating and screwing things up?
Right. No, it's an absolutely good question, and it's a non-trivial question. It's not just like a pesky little detail to work out. Sometimes it can actually really falter algorithms. Your algorithms can really truly fail because you fail to take into account that you never actually had infinite precision estimates of the input that you're working with. So it's true that I guess many papers that work with such statistical models, or whatever, like real number inputs in general, they rely on like some reasonable assumptions, like say maybe the kind of operations that we're doing in our algorithms are likely gonna generalize to even rational approximations to the input, and therefore they're gonna work fine. So it's true that there are many papers who may not be taking care of these details in the most transparent way possible. On the other hand, I think the core treatises of computing on real numbers, let's say for example solving semi-definite programs or convex programs more generally, which is like one setting where you encounter computation on real numbers very seriously, they were really, really careful in taking care of these issues. Like for example, this what many people would describe as the textbook is this book that three great people wrote, Grushel, Lowash, and Schreiber. It's like 40 years since they wrote a book, but it's still the best book to read on the topic. And they're extremely careful in the sense that they took care all the details about how you might be computing with real numbers. And maybe we should talk about how you actually do that for a second. So like there are two ways to deal with real number inputs. There are first of all no real number inputs on digital computers. There are no real number inputs on Turing machines. So it's just like even if you have real number inputs, you've got to like transform them into rational approximations with like finite number of bits or whatever, right? Now the one natural and standard way to do this is to just take good enough rational approximations and then show that your algorithms works with these rational approximations. And then here's the most careful part. Many times when we analyze and design algorithms, we assume that basic operations are going to be, whatever, order 1 steps or order log n steps. Like, for example, you add two numbers, you think, well, okay, it's going to be easy. Multiply two numbers, it's going to be easy. But the details now actually matter. It's precisely the kind of details you were hinting at, right? Like, if I multiply k-bit numbers, the exact result would be like a 2k-bit number in general, right? And so if I have like k bits of precision in one and k bits of precision in the other, if I have to store the exact result, my precision actually grows. And now you could imagine that your algorithm basically like multiplies like a sequence of numbers and really relies on like some far off digit. If it does something like that, your algorithm, even though the number of operations, arithmetic operations it does is like, polynomial, even linear for that matter, it could be that the bit precision that you need to do these operations with actually grows exponentially. And then it's no longer polynomial.
This is the same as like, when we do exponentiation, actually the length of the input grows exponentially.
And grows like multiplicatively. And so, if you do like, let's say n steps, you're suddenly in like exponential land. And it's not a theoretical question at all, by the way. I mentioned this algorithm for solving linear equations before, Gaussian elimination. It's a very, very simple algorithm. It basically, what it does, it finds an equation. It, makes one of the coefficients equal to like, you know how you solve equations, right? Like you add a multiple of the first equation to all the others, and you try to cancel out one variable, right?
Right.
It turns out that if you do it in some straightforward way, you hit numbers of exponential bit complexity. And that's why, it requires some, reasonable amount of care to, describe an algorithm that will actually achieve polynomial time complexity when the inputs are, rational numbers. Okay, so that's basically that. It at least shows that we've got to be careful about this. And it turns out that, when we are imagining Gaussians or statistical inputs, I think we are imagining rational approximations to them. And our algorithms are supposed to argue for the bit complexity, just like in Gauss elimination we had to. It's true that maybe not all papers are doing it. I guess most of them will work fine. That's maybe the underlying assumption. Some of them won't. For example, there's a paper that I'm writing right now with, your head TA, which really relies very strongly on getting these details right. Yeah, that's shout out to Misha Ivkov, And so watch out for this theorem and the complexity details.
It's coming, okay. So maybe that's we can talk a little bit about, like, you've worked with some undergraduate students in research. So I'm sure some students listening to this are wondering, like, hey, I'm interested in theoretical computer science. One day I want to get into research. What's the best way to get into theoretical computer science research? If you're right now, let's say, freshman, sophomore.
Yeah, I think CMU in particular is fantastic in the amount of resources it offers to, early stage undergraduates. So I guess my first advice, which is perhaps maybe everybody's advice, is to take maybe advanced classes. And thankfully we have several of them. At that stage, I would not recommend over-specializing. So I would maybe suggest being equal opportunity offenders and take complexity theory classes and also algorithms classes, and perhaps even machine learning classes for that matter. You don't know what you're interested in.
Right.
You probably want to go broad.
Right.
Maybe in one of these classes, the benefit of taking advanced classes as opposed to, introductory classes is that you get to learn what might be happening at the bleeding edge of research. And so either you would learn that, hey, that's boring, I was fascinated by this 251 class by Professor Ada, but, I hate this. And that's great.
Yeah.
You at least realize it.
Absolutely.
And alternatively, you might realize that here's a class of problems I really like, and I think the techniques are, enjoyable to me. The results are fun to me. And then, you basically approach the instructors, and I'm sure they're always happy to talk about that further. For example, I guess there is a little bit of an advertisement I can make, Anupam Gupta and I will teach a class on modern approximation algorithms in the fall. It's one of those advanced classes. It will be a fast-paced class, but you'll study more algorithms at the bleeding edge.
So what is the prerequisite for this?
That's a good question. I think 451 for sure. I can imagine that people with 251 knowledge could try to get by, but I can imagine it also being hard. 451 would be, I think, would be great.
Do you expect to teach this a year from next fall again?
I definitely expect to teach some version of that class. It's not clear if I will teach the same class.
I see. Because I think for students currently in 251, maybe not next fall, but the fall after that.
That's a good point. I always teach a class on, some form of approximation algorithms, the flavor varies, the kind of problems varies. So I can totally imagine a version of this class. It may not be the same, but I don't even think it would matter that much.
Yeah, great. I think I agree with your overall suggestions there. General courses, I think 451 is a good target. Take it as soon as possible.
Yeah.
And that can be a stepping stone for then graduate level algorithms courses.
Right. The other thing actually that, these opportunities are maybe somewhat more new, but, there are all these summer schools and programs for interested undergrads that are beginning these days. For example, this summer, there is a New Horizons school in TCS.
Yeah.
Some of my students in 455 are actually, they've applied and I hope they get in and, get to participate in this program. And I guess, my suggestion would be to, basically look for these programs.
Opportunities. Great. Let me ask you, Yeah, we're running out of time, so maybe it's like more like a lightning round.
Sure.
Okay. I wanted to ask you about the general state of TCS, theoretical computer science research. When you look at, let's say, the top conferences, the papers being published, are you generally happy with the state of the field? Do you think there's room for improvement? If there is, what can we do better, do you think, as a field? Yeah, let me get your thoughts on that.
Yeah, I would say I'm generally happy. I think as a field, we are reasonably healthy. But like any scientific field, I think there are complaints, legitimate complaints that people have. Some people might think that the conferences are focusing on some areas, not as well as others. Mm-hmm. Some people might think that the kind of papers we are accepting or like favoring are maybe not the right kind, or maybe our balance is not quite right. And all of those complaints, I think, are legitimate and valid. But I would say, they are maybe they've always been there. Like, I think if you talk to people like Avi Vigderson or like Omar Reingold or Oded Goldreich, who've been there, like who are like in some sense more senior and advanced people in this field, they would tell you that, these questions and these issues and these misgivings about, potentially things that need to be improved have been there all the time. And, in that time, TCS has made like great advances and great contributions. Yeah. So it's not like, in some sense they're hurting the bottom line, so to speak.
Right.
So there are always things to improve. I have my own gripes, and, you should see me after my papers get rejected.
Next time I'm going to time this interview right after you get rejected, but let me know.
Yeah, but I would say broadly speaking, I'm quite happy with the way the field is organized. It's very approachable. Mm-hmm. The experts are very easy to talk to. The problems are well motivated. The techniques are interesting. And I think in general, the field is very outward looking, which is the fact that I, really enjoy about TCS. Like, when we look at biology, we don't say that's not our field. We say, well, give me your problem.
Yeah.
It's possible that, we don't say the most intelligent things all the time. It's possible that we invent our own problems and call it biology at times. All of that is probably happening. But sometimes we do say things of relevance to biology. And, at times, these kind of things actually led to the whole field of computational biology, to be honest, right? Mm-hmm. Same thing about game theory. We don't say that's not our field. We say, okay, give me your problems. We'll see what we can say, right? And it's very outward looking, very very open kind of a philosophy that the field as a whole has. And I think that's one of the most exciting aspects.
So there's a lot of diversity, I guess. And then when there's so much diversity, there's going to be disagreement on what to focus on and how to do research.
It's part of a healthy scientific field that there are disagreements to the directions and the problems and the techniques and.
Yeah. So I got this question from one of the students, and I thought it was very interesting, and I'll ask you the same. So let's say you have $1 billion to invest in theoretical computer science research. Where would that money go? How would you... I know you love your own research area, but maybe don't put it all in your... Yeah.
Yeah, I guess this is maybe equivalently a question about what areas that I enjoy the most, maybe, and maybe
what which areas do you think are promising,
like one area that thankfully is getting a lot of attention now, so maybe it doesn't need the $1 billion or any part of it, but quantum computation would definitely be one of them. Mm-hmm. There was this time when, only the true believers did quantum computation.
Right, yeah.
But now I think everybody does it. So I would say quantum would be high on my list. I would even say, there's this area which is like maybe slightly, down in the weeds and, maybe doesn't come out in introductory courses very much, but it's this area of fixed parameter tractability. We don't talk about it too much.
Yeah.
But, in some sense, I think it has beautiful ideas, beautiful algorithms, beautiful lower bound techniques. Mm-hmm. And it actually tells us how the problems that might look hard are maybe at times not so hard.
Yeah.
Like for example, for several of the NP-complete problems, there are these so-called fixed parameters, such that if you think of algorithms where you basically think of those parameters as fixed, you can come up with like really efficient algorithms. Right. And, those are at times very, very useful. Mm-hmm. And I guess I mentioned FPT only because I don't see enough talk about
I
it.
see. Okay.
And so maybe, yeah,
I see.
those will be the two that I'll talk about.
How about, what do you think about the advance of machine learning AI? And I want to particularly ask about how do you think this will affect mathematical research in the future? Do you see more and more like computer assisted proofs coming in? Do you see our role diminishing over time?
I mean, first of all, I guess I'm mostly, I'm not like worried about it. I'm actually mostly excited about it.
Yeah.
I would like to see a day where algorithms are boring.
Yeah.
Where we don't have to, teach an algorithms class and like talk about all the clever and creative ideas we have to come up with to solve problems.
Yeah.
It would be great if like, algorithm is like, you go to Mathematica and it comes up with an algorithm. That would be great.
Okay.
It would be, that would be superb. I don't see that we are quite, anywhere near that stage yet. I think, in all areas of science, I think computers are assisting, and even in mathematics, I think computers are assisting very, very well. I can see that role growing. I can see that computers being helpful to us in like maybe demolishing conjectures or, coming up with counterexamples, and at times even coming up with fragments of proof. And I think that's very exciting. Like even though it might appear like it's not, doing mathematics or whatever, I think it's an extremely, extremely exciting advance.
Yeah.
Maybe that's the level of expectation I have from how AI would affect how we do mathematics and computer science in the next 10 years. But, there are people who are more optimistic than me on those things. And maybe, it will be even more exciting.
Yeah, I mean, there's a lot to say there, and like how computers are coming in these days. SAT solvers are very interesting, and would love to talk about that. But okay, very quick questions since we're coming out of time, running out of time. So, do you have any general advice for our undergraduate students? When you were at that age, was there something particular that you would have liked to know?
Yeah, I guess times have changed so much. This is a complaint that I guess I've made.
You're not
so
that
much.
old.
Yeah, but still, like I finished my undergrad degree in 2010. I joined in 2006, and things were very, very different there. Like I guess this is a comment I've often made in grad admissions committees. Like if I were to apply today, I won't make it. And it just like undergrads are like so much more learned and interested and curious, and they just know so much more. So I guess my advice would be that unlike in our stages where it was maybe relatively quiet, not that much happening, at least that was how my undergrad was, it's very different. And there might be a danger of like information overload or like stimulus overload for people at early stages. Like there's so much excitement,
Right.
AI, machine learning, theory,
Which
whatever.
one do you choose?
What do you do, right? Like, and there's a chance in which, you could basically get overwhelmed. And so I guess maybe this is a outdated advice, but I guess, maybe I'll go back to a little bit, maybe not like 2010 all the way, but I'll go back to like 2012, 2013 levels of stimuli.
Yeah.
Where, people still take a time to, maybe not focus all on like blogs and whatnot, and like maybe come back and still, do the hard work of reading textbooks and, thinking about research problems for hours.
I mean, going to a library, finding a paper.
That doesn't happen anywhere, right? I'm not sure.
That's one of the greatest joys.
Yeah.
That doesn't.
I actually don't know. Full disclosure, I've never been to the CMU library yet.
I mean, sorry to say, you might be disappointed because I've been, and there are no books in libraries anymore, apparently. It's just study spaces and everything is online.
Oh, no.
Yeah. So it is, because like one of the things that I love about libraries are so inspiring. You're surrounded by all these books and all this knowledge, and just going there studying is very inspiring. It's a different...
I also, again, like, this is probably a problem that people who, are younger won't really have. But, I really like the feel of like a journal or a magazine in my hands.
Yeah.
Sometimes I pay overly big price to actually have that, even though the digital access would be like so much more cheaper.
Yeah.
Libraries used to be like sources for that.
Good old times. Old times. Okay. Well, let me ask one more question and we can end with that. You're obviously a very successful person, but, along the way, What would you say like was your biggest struggle or maybe a failure, and how did you overcome it? How did you deal with it?
Yeah. First of all, like, I have to say, like, it's people obviously don't talk about their failures as much, but there is just no one I know who hasn't had several of them. Like, in some sense, the hardest part of answering your question is like which failure to pick.
Yes.
But I guess maybe one thing that might be relevant to this discussion is like, times in grad school. And, grad school is usually reasonably stressful for, just everyone. I just don't know anybody who it hasn't been stressful for. Mm-hmm. It was stressful for me. I started out doing computational learning theory. My advisor, Adam Clivens, was very interested in that area at the time. And, we wrote a few papers, etc. But, maybe around my second or maybe beginning of third year or whatever in my PhD, I felt like I'm not enjoying it so much. And I did this internship at Microsoft Research India. And I got interested in a completely different area where, I was analyzing linear programs and semi-definite programs. And, I didn't do anything. I didn't really prove anything that summer. I came back and I really got interested in this, a big open problem at the time. And I spent like a whole year. So like, it was like, I was beginning my third year. So it was like, by the time I was ending, this was like in the middle of my fourth year, I spent a whole year on trying to attack that problem. And I had some ideas and, but we were nowhere close to, resolving it. I sucked in my advisor into this work. It's like my advisor was also like spending times in meetings and we were trying to prove this. And, I think summer of 2014, I might be like off by 1 year.
Okay.
It's all, but somebody else solved that problem and, it was like brilliant solution and we were nowhere near it. Mm-hmm. But here I was like, I had like a reasonable career going where I was like, writing papers about computational learning theory. And I suddenly like said, okay, I'm not interested in this. I flaked out, started doing like a completely different area. And I had nothing to show for it.
Right.
I was pretty down for like a few months and I thought, well, maybe this is just too hard and, I'm not good enough to do it. Yeah. Oh, certainly. Yeah. I think I never really thought that a career in like theoretical computer science research was for me until like maybe my 5th year in grad school. Like till then I thought like I'm enjoying it, might as well do it. That was the best feeling I had. The worst was like, well, I'm not good enough for anything. So I think the first few years of grad school, they were like, I was not unhappy or anything, but I was also not like very optimistic or bullish on my own career.
And what got you out of that mindset?
Yeah, it's very, it's hard to like pin like a single event. One thing, I guess my advisor was of course like super helpful. He always thought that I was doing better than I thought I did. Mm-hmm. And like one thing that helped was like, he used to, tell me to go talk to other people. It's like, he said, hey, you're thinking about these problems and maybe you want to talk to other people who are thinking about similar problems. And so, at some point I visited, Professor Prasad Raghavendra at Berkeley, and I visited like, Boaz Barak at Harvard. And I got talking to people who were like, doing a lot more problems of the same sort that I was interested in thinking about. And, at some point I actually did manage to prove something. And that was great, and I suddenly thought that, hey, I'm not maybe that bad after all. Yeah.
I think that's an amazing advice. I try to give this advice to students starting grad school as well. Talk to people. It's also like much more fun that way.
Yes.
Right? We're social beings. It's
yes.
like working together. This is not a competition. This is a cooperation and to advance science.
Yes.
So, I think that I love that.
And thankfully, I think, this is what I was, I guess, also alluding to earlier. As a field, theoretical computer science has thankfully several such people. In fact, it's hard for me to say, it's hard for me to point out like a person who did not, feel approachable and like was helpful right off the bat. All these people, were like busy people doing their own research, but they never like turned me down. They talked to me and like eventually became my close collaborators.
Yeah.
And that is what I envision, I think, would happen to, anybody starting out in theory today.
Exactly. I agree with that. Well, on that note, thanks a lot, Pravesh. I think we could like talk for another 10 hours, but this was a lot of fun and thanks for coming. And then, let's, I have some Turkish kebab here. So let's have some.
Yeah, this was like super fun. Yeah. Thanks for having me.
All right. Thank you.